Hello and welcome to today's class. For today, we'll be trying to derive the slope equation and the deflection equation of a cantilever beam with uniformly distributed load, that is UDL, using area moment method. I have actually drew a video how to prove for deflection equation and slope equation of a cantilever, but using what the double integration method. So I'll drop the link to the video in the description of this video. So check the description, you see the link that will take you to how to prove for a cantilever beam using double integration method, right? But for this case, for today's class, we'll be dealing with cantilever beam with UDL or perhaps uniformly distributed load, but in this case, using area moment method. First things first, we said whenever you get the word cantilever beam with what the uniformly distributed load, your first task there is to draw a diagram. So for my diagram here, I have a cantilever beam, of course, something of this nature, a cantilever, something of this nature, with what a uniformly distributed load. Of course, this is my uniformly distributed load in this case, right? I have a span of length L. Here becomes my entire length L, and this become what my weight in what the kilonewton per meter. All right, I have the diagram illustrated here. I'm taught to derive the I'm taught to derive the slope equation and the deflection equation of this man here. My first task is to draw the diagram of the deflection of this beam. So for my diagram here becomes something of this nature. For a deflection, when this weight is more than the beam, it deflects in this manner. So I have a parabolic curve here in nature, right? So something like this, of this nature. Hence, I'll pick a point here. I'll call that point G, such that I will trace the point outside this way. I'll call here 3 over 4 3 over 4 L. I have this one here and this. That is, the center of gravity for this figure here is simply 3 over 3. It falls at 3 over 3 of the distance L, and I have that my entire height here is going to be WL squared over 2EI. Your task here is to master the diagram. Just master this diagram, right? That's your first task there. So the deflection of this beam, when this weight is more than the beam, it deflects. It's just like you're buying a bread and you're putting a block on a bread. So it's like putting a bread, a block on a bread. You know what that means? It means that the bread will cut, right? Because the weight of the block, the bread cannot withstand the weight of the block, hence it deforms. So it means that if this weight here is the value is higher than the beam here, it deflects in this sense. So let's calculate for slope equation. That's A. For area moment method, we said is A. So in this case, my A is equal to, look up please. My A, when I derived the slope equation for cantilever beam with point as free end, the area was what? 1 over 2 breadth times height. In this case, it changes. Why? Because it's what? UDL. Because what the 1/3, 1 over 3 times breadth times height. It means that my slope, which is A, is equal to 1 over 3 multiplied by my breadth. What's my breadth in this case? My entire length is my breadth. That's L multiplied by height. My height here is what? WL squared over 2EI. This means that if I multiply through, I'll have that my slope, which is A, is equal to L times L squared is L cubed. Pick out W next up L cubed, all over 3 times 2 is 6 EI. So this is like my formula, or perhaps my slope equation for calculating a cantilever beam with uniformly distributed load using area moment method. All right, from this concept here, let's derive the other concept for the deflection equation. So we said for deflection equation, y, we said multiply your slope equation, or perhaps let's say calculating for the deflection equation. So that's y is equal to, we said multiply your area or perhaps your slope equation, that's A, by center of gravity, that's G. So this means that my y is equal to, what's my area or perhaps slope equation, that's WL to power 3 all over 6 EI. Multiply this guy here by G. What's my G here? 3 over 4 L as my center of gravity for the deflection. Yeah. All right. From here, what will I do here? I'll multiply numerator and denominator at this point here. All right. Let's take a past question and let's see how we can use the question to solve problem using this idea. All right, guys. Your task here is to write out the question and copy them down, and let's solve this together using the idea of what we just learned now. All right, let's solve this together, please. The question says, a cantilever projecting 2.5 meter from a wall is loaded with uniformly distributed load of 8,000 kilogram, full stop. Determine the moment of inertia of the beam section if the deflection of the beam at the free end is 1 centimeter, right? Take E to be 2.05 to the power 6 kilogram per cm cube per cm. All right. Is this cm cube? All right. Is cm there? All right. Look up, please. First task is to write out the given parametric unit. So solution to the question. Solution. What am I given there? First task there. I'm given a length. A cantilever projecting 2.5 meter from the, look up. This is a wall here, projecting what? 2.5 meter. That's my length. So my L there, length L is what there? 2.5 meter from the wall is loaded with what? Uniformly distributed load. Look up with what? Uniformly distributed load of 8,000 kilograms. So my weight there, weight, that's W, is equal to 8,000 kilogram. Next up, determine the moment of inertia, that's I. So I'm looking for moment of inertia. So moment of inertia, that I is unknown. I is unknown, right? Of the beam section. If the deflection, what's deflection? That's y. So I'm giving a deflection y is equal to what? 1 centimeter. All right. Taking E, I'm given that E is what there? 2.05 times 10 to the power 6 kilogram per cm, right? Per centimeter, or what have you. All right, let's solve this question together, please. I'm given length, weight, moment of deflection, and E, which is Young's modulus. Wait, hang on. W is weight, L is what? Length. E is Young's modulus, I is inertia, moment of inertia. So in this case here, I'm given Y, deflection. I'm looking for what there? I. It means that if I take this one here, I'm given Y. I'm looking for I. Check, look up. Am I given W? I'm given W. Look up again. Am I given length? Of course. Am I given E? Of course. It means that I can use this one here to look for my moment of inertia. So from here, all right, from here, record that we said that Y deflection is equal to WL to power 4 over 8EI, right? Over 8EI, yeah. I'm looking for I. All right, I'm looking for I. The task says just swap this one. Pick I outside first. So I have that I is equal to WL to power 4, this one, all over 8E. Take I outside, take Y back here. I have Y here. So it means that what's W? That's 250 multiplied by, what's my length there? sorry, W is 8,000. Yes, 8,000 by my length. What's my length? 250 all to power 4 all over 8 multiplied by E. What's E there? You just only loss, which is what? 2.05 times 10 to power 6 multiplied by Y, which is 1, as given below here, above here. So that I have that I, which is moment of inertia, is equal to, if I multiply numerator, that's 8,000 times 250 to power 4. I have 3.125 times 10 to power 13 all over multiply denominator 8 times 2.05 times 10 to power 6 times 1. So I have 16400,000. I have this. Divide numerator by denominator. That's 125 times 10 to the power 13 divided by denominator there. I have 190548.7.8. What's like my SI unit here? Right? What's my SI unit here? All right, the SI unit here becomes what there? Cn to power 4 as my SI unit for moment of inertia. So that will work on this, right? So we found this class helpful. Do not hesitate to share, like, and leave a good comment in the comment section. And if you have any question, you can simply ask in the comment section. I will reply you as fast as I can. All right, thank you and welcome to Excellent Link Academy.